If you're watching this video, it probably means that you missed our classroom discussion on modeling with quadratic functions. So the plan in this video is to walk you through step by step what we did in class so that we can get you caught up and you can get an idea of what we did. It's not a major focus of what we'll do, so you didn't miss on anything big, but it's a nice little look into what we can do with some values, some data points. So if I go too fast at any time, feel free to pause the video and rewind until you're ready to continue along. So we're going to jump in and we're going to look at a scenario called the pumpkin fling, which in South Dakota is known as pumpkin chunkin'. And there's a video here if you have the time. It's about 2 to 3 minutes long, and you can see some teams that have built some catapults and are competitively flinging some pumpkins across a field. And so, what we do with modeling data is we actually look at a scenario. So, we are looking at some data points that are collected by just watching something happen. And so, in this case, we are going to look at two variables that might relate to the pumpkin contest, this pumpkin chunkin contest. And that might be that the angle a pumpkin is released and how far the pumpkin ends up flying. So in this case, we have some data points that involve angle measures of 20 through 70, counting by tens, and then various distances that the pumpkin flies through the air. And so we need to look at some things here. One, there are other angle measures that we could talk about, but those are angle measures that just weren't observed by us. So we didn't watch what happened when a pumpkin was flung with an angle of 45 degrees, or we didn't get to see how far a pumpkin went when we released a pumpkin from 32 degrees. And so part of what we're going to do is what's very common in statistics is we take some observations, and this is not a lot, but we look at some observations and then we try to figure out a pattern that we can apply to other values that we didn't get to see, but we could then get an idea of what would happen if in this case, a different angle measure was used. Okay, so this is going to greatly relate to what you did in previous courses with scatter plots and finding lines of best fit, where you tried to guess where to draw the best line through all the points. I'm going to show you today how to do that with Desmos. So one disclaimer is these are not actual data points. We fabricated these to make them go along with our discussion a little bit easier. But this is a scenario that would probably apply to what we want to do here today. So let's go ahead and jump into this that says about using Desmos. And in this case, we could follow along with the steps shown here. I'm going to deviate from them just slightly, but Desmos is a very user-friendly calculator, and it's very nice to have access to. So what we are going to do is we are going to put these values into our graphing calculator. And one thing to recognize is that we are going to use our angles as our x values and these distances as our y values. So if you hop over to desmos.com, we're going to use the graphing calculator, and you can either choose the big button in the middle or you can go to the math tools and choose it from there. Either way, let's go to the graphing calculator, and the first thing we are going to do is we're going to add our table, and there's a plus sign up here that says add item, and if you choose the table icon, you'll be ready to go. Okay, and our table, we see that we have x values and y values, and we're going to learn a little programming as we do this as well. So x1 is going to be the name of this column. So all of these numbers are going to be stored in x1, and y1 is going to be the name of this column that we're going to put our y values into. So let's go ahead and get started there. I know I had x values of 20 and 30, and if you hit enter, it's figuring out the pattern that I was counting by tens. Okay, and so I have my x values ready to go. I need those y values as well. So let's go ahead and type those in. For the 20 degrees, we had a distance of 372. 30 degrees, we had 462. For 40 degrees, we had 509 feet. 50 degrees, 501. 60 degrees, 437, and 70 degrees, 323. So there are 6 ordered pairs in our table. Those are our 6 data points we're going to work with. And when you type them into the table, Desmos should end up graphing those on the grid. In this case, though, we can't see those points because our grid is only looking out to 10 in this direction and about 7 in the other direction. And these numbers are much larger than that. So now that we have our data points put in, we are going to change our viewing window here by going to the graph settings, the wrench, and we're going to change how far we can see on the x-axis. So right now we can only see out to 10. I see an x value that's 70 at most, but we might need to work with a little bit bigger numbers than that later. So good ideas are to jump a little past your largest value, give yourself some wiggle room. So I'm going to jump out to 100. And so now we see the x-axis is letting me see much farther. We're going to do the same with the y-axis. Rather than using this value of 6, we see that the largest y value in our table is 509. We might need to work with something a little bit bigger than that, so give yourself some wiggle room. I'm, in this case, going to jump up to 550. And when you do that, you're going to notice that your values are appearing here. So here are our 6 data points in this table. Okay, so let's go ahead and get back to our screen here. We need to write in what we have used for our maximum x and our maximum y values in our window. So for x's, we change that maximum to 100. And for the y's, we change that to 550. Okay. So something else we're going to do in our table, what's different today is we're not just graphing random x and y values. Our x and y values represent something. So in this case, recall that our x values are angle measures. And that's in degrees. Remember, the y values in our table were distances. And it's good to know what your distance is measured in. Feet are much different than yards or miles or meters. Okay, so what we want to do is when we make graphs, we want anyone to be able to look at them and know what's going on. We're going to add those labels to our graph. And so here, I'm going to go back to graph settings. And when we click on that, we see there are some boxes down here for adding labels. It's a very easy step to do. For our x-axis, remember that was angle in degrees. Oops, wrong slide. Angle in degrees. And our y-axis label was distance measured in feet. And you see right away that those labels are showing up on the x and the y-axis. One last thing I'm going to do, I like to see a little bit below my x-axis, have a little wiggle room there. So I'm going to change this y value to be lower than that. I'm going to go to negative 10. No, I'm going to do negative 20. That's just visually, we can see underneath it, we can see the scale down there. Just kind of cleans it up a little bit. Not something that we needed to do. That was just personal preference. Okay, so we have our labels here. We have our data points ready to go. We have a good scale. We can see everything. One thing for us to notice then is how these dots are arranged. And so you might be looking at these points and see that they kind of curve. And that's something we've been working with recently. These graphs that go up and back down. And so that's the idea of a parabola. And what we are going to do is find an equation of this parabola, the best one possible to go through there. So rather than me guessing that, I'm going to have Desmos figure this out for me. What parabola is going to go through these points the best? So we have some steps here in our worksheet. If we go to the back page, But actually, before we do that, I realize the worksheet has asked us to take a screenshot on Google Classroom. So let me go back to our graph here. Let's delete this parabola. We don't want that right now. A screenshot is very easy to take. This might be something you've done before. I'll pull it up here so you can see it. For a screenshot, you have two options. You can do a full screenshot, Control plus the switch window button at the top middle of your Chromebook, or you can use Control plus Shift plus that switch window button, and that does a partial screenshot where you can just crop a certain portion. So if you just want to take a picture of part of the window, you can click and drag and do that, and it will automatically go in your downloads folder. Okay, so let's go ahead and go here. Let's take our screenshot. I'm going to do a partial screenshot. Make sure you're including your table and your graph. Oops, I missed a little bit there. Let's try that again. So again, include the table, the graph, your labels. One last time. A little glitchy on me. So table, graph, and there you go. And we'll insert that into Google Classroom when we're done. Okay, so let's jump into what we're going to do next. We are going to find the best model for our equation. So we saw those dots. We saw that they don't lie in a straight line. They are in a curved arrangement, meaning a parabola could be a very good option to try to draw through them. And a graphing calculator is going to find the best one possible. So just a reminder to you, and this should look familiar, equations of quadratics, the standard form of them is y equals ax squared plus bx plus c. Very commonly, we see these quadratics that have three terms, where there's a coefficient a that's always with x squared, coefficient b is with x, c is a constant coefficient that never has a variable with it. And we are going to tell Desmos that we want something that looks just like this, something that has three terms with it, an a, a b, and a c. It's got this x squared. And it's going to involve a little bit of programming on our part because we need to tell Desmos what we're talking about. So a little typo here. This should be a tilde instead of a equal sign. But essentially what we're going to do is type this in, and I'm going to explain that to you as we do it. So we're going to hop back to Desmos, and we are going to insert an expression. Okay, and so what we're going to do is we're going to tell Desmos to give us the equation of a parabola that goes through these points. So the way we're going to do that is we're going to still focus on that format of y equals ax squared plus bx plus c, but we need to be a little detailed in how we tell Desmos to do this. So one of those things is we're basing this equation off of our points that we have on the grid. So when Desmos is finding a good graph that might work with these points, we need to tell it where our y values are. So if you remember, we have all of our y values stored in this column y1. So we're going to not just put y, we're going to put y1. And Desmos is realizing what we're talking about. It sees that we have a 6-element list, meaning we have 6 y values in this column. And we're going to have Desmos do an approximation. So instead of using an equal sign, we're going to use this tilde. And that should be in the upper left of your keyboard, just below the escape key. And so we're telling Desmos to use these specific y values that we've labeled as y1 and to find an approximation for us. And now we want to tell it the format that we want. We want this quadratic format in this way. So we want an a value, so we simply type a. We want to have an x squared, so we start by typing x, but remember our x values are stored here in this column that's been labeled as x1. So to tell Desmos that's what we're talking about, we're going to put x1. And if you simply type a 1 after that, it drops down. And so we just told the calculator that we want these x values. And then we need to square this, and you can either use the keypad on Desmos itself, or if you hit Shift 6, we can type in an exponent of 2 and then right arrow out of it. And so Desmos is starting to try to figure out a good equation, but we haven't given it the full format yet. So we need to keep going a little bit here. We're going to type in plus b. That's our middle coefficient that always has an x with it. But we can't just put x. We need to tell it where x values are. So we put x1. And then we're going to end with that third coefficient, which is plus c. And now that we've typed in the format that we want, this quadratic model, we call it, that has 3 terms, we see we have a pretty good graph going through everything. And so one thing that we should never expect is that we're going to get a graph that goes through every single point that we have. Now this one is very close, and that's very unlikely, but it's nice. It's a nice scenario to have. This parabola is going through almost all of these points and almost going through them pretty perfectly. So this is a pretty good graph to go with our points. Now, what the calculator is doing, it is taking our suggestion, use a quadratic with 3 terms, and it ends up telling us what our coefficients A and B and C are right down here. So it says parameters. That's based on the values we told it to give us, and it's telling us the best A value, B value, and C value to use in this particular situation. And so that's what we're looking for here. Those A, B, and C values we're going to record, and that is simply just, let's just round those to 3 decimal places, just for the simplicity of it all. So negative 0.261 was the A value. B should have been 22.591. And C is 23.029 if we round it. And we should all get these same values, okay, because we're all working with the same calculator and the same points. So if you have something different, go back and check your data. Okay, and so we need to understand what just happened. We were given an A, a B, and a C value by the calculator, which should help us write an equation, because we know what we wanted that equation to look like. We wanted it to look like this, an ax squared plus a bx plus a c. And so that's what's been given to us, and we're just going to write an equation that looks like this, except we're going to substitute in our values of a, b, and c. So we have y equals, it says ax squared, so we have an a value now of negative 0.261 x squared. B is right there in the middle, so we have plus bx, which is going to be plus 22.591x. And we have plus c, which is plus 23.029. So this equation here ends up being the best possible equation for our 6 data points. So this parabola that we're seeing right here has the equation that we just typed in. Okay. So one more question up here is to look at the r squared value. And we're not going to talk about all this stuff much after today, but it is nice to see it, so you get a little exposure to these ideas. R squared serves a purpose, and we're told that the closer it is to 1, the better it fits the data. And I'll give you a brief explanation for that, but let's go find it real quick. It's right up here with your other parameters. We have a statistic r squared that says r squared equals 0.9993. And so let's go ahead and record that. So 0.9993. And the question is this a good fit? Well, the answer is yes, it's a very good fit. One, we can see it visually. This parabola is almost perfect for these 6 data points. But for another reason, this R squared value represents a percentage. It represents the percent of the data the percent of the distances for the pumpkins being thrown. What percent of those distances are explained by the angle values? And this as a percentage is 99.93%. So R squared is telling us that 99.93% of our distance calculations can be explained by um, the angle of release. And 99.93% is about as good as it gets. Obviously, maximum is 100%. So we can't get much better than this. So if you just want to be very basic about it, you can say yes. But the question of is it a good fit? You could say yes, very much so. It's almost perfect. It's almost perfect. 100% would be perfect. Okay. And now that we have all of that, we are going to take a screenshot of what we have. And you don't have to submit it into a document here. You can just do it separately in Google Classroom. So let's get that screenshot again. Either control in the switch window, or for a partial, you can do control shift in the switch window. Click and drag over the parts you want. Show your equation, your model, your table, and your resulting graph. And just like that, it will go directly into your downloads folder. Okay. So now we have a few questions that we're going to answer about this graph that we made. So remember what we just did. We started with points on the chart here, and then we ended up finding an equation that goes with those points, which is the direct opposite of how we normally approach these things. So some familiarity here, we're going to analyze our graph that we now have, and we're going to talk about some familiar things like a vertex. So a nice thing about Desmos, and good news, it still happens. When you make these graphs, it tells you the points of interest. So if you click on this parabola, you're going to see some gray dots appear. One of those gray dots is your vertex, which is the turning point of your parabola. So we have a vertex here of 43.208, 511.09. So let's go ahead and put those into, put that point on our list here, our vertex we have. So 43.208, 511.09. Okay. An axis of symmetry, just a reminder to you, is that line, that dividing line on a parabola that would create two equal parts of the parabola. So it's going to go here. So we should have two equal parts on either side of this dividing line. Where would we have to draw such a thing? Well, we'd have to draw it through the vertex. So remember that a vertical line always has an equation, and it's always x equals a number. So we're going to use the x value of our axis of symmetry. So for here, we have an axis of symmetry. And I think I said x-axis of symmetry. It's the x-axis of your vertex. So we have x equals 43.208. Okay. And then we could talk about, does this graph have a minimum or maximum? Because it has a highest point. The vertex is the highest point on this parabola. That would be a maximum. And again, the maximum is how high up the graph goes, which is a y value. So our maximum is the y value of the vertex, 511.09. Okay, so there are some other points of interest here that we're discussing, the y-intercept and x-intercepts, and those are also shown on the grid. So if we click on the parabola again, these gray dots appear. The y-axis, the y-intercept is on our y-axis, so we can click there, and we see its value, 0, 23.029. let's go record that. So 0, 23.029. Okay. And you might notice that was our C value from before, which is always going to happen for us. And now we want our X values. So we go back to our graph. We'll get rid of that Y value here. We'll click on our 2, in this case, X values. So we have an X value at -1, 0.008, another at 87.423, and we are going to record both of those. So right here on our x-intercept blink, let's put both of those points down. We have a -1, 0.008, and we had the other point, 87.423. 0. So two x-intercepts, and if you remember, our solutions are directly tied to our x-intercepts. Our solutions are the x values from the x-intercepts. So we put the braces to signify we're listing solutions, and we had 2. We had an x-intercept at -1.008 and another at 87.423. And something to note here, we are not saying this is a point. We are just saying we had 2 different solutions. Okay, and so one last task for us to tackle is the domain and range. And this is going to be a little bit different than it has been. We normally, for domain and range, incorporate infinities or negative infinities. But for a word problem like this, it doesn't quite make sense. So when we talk about this particular application, we could talk about the domain of our x values that would make sense for flinging pumpkins. And so we have x values that are the angles on these graphs, the angles at which the pumpkin's thrown, and some of them make sense. Most of them make sense, but I think you'll find that negative values do not make sense. We don't throw anything from a negative angle. That would mean that we've gone underground before we ever released it. So the lowest x value that's going to make sense in this scenario would be 0, an angle value of 0. That's the first number that is non-negative. So our domain is going to be a little different here. We're going to start at 0, and we're going to end with the highest x value that we're talking about. And so out of all of the x values that were being shown, what's the maximum x value that's being used by this parabola and still makes sense in our situation? And if you go all the way to the other side of the parabola, this is the last point here before we go back into the negative numbers. And that point is the x-axis, x-intercept we wrote down earlier of 87.423. And so let's go ahead and record that. The highest x value used in this scenario is 87.423. So within this interval are all possible x values in this particular model. So we're not going to talk about negative angles. We're not going to talk about an angle of infinity. Neither one of those would make sense. And we're going to do something similar for the range here. The range is your y values, which is the distances that the pumpkins get thrown. And I think you'll agree that the pumpkin will not get thrown negative feet. And so that means the least distance a pumpkin will go is 0 feet. And the farthest it gets thrown, remember, in our graph, the largest distance is going to be the highest point, which is our vertex. And we already know where the vertex is. So our vertex we see had a height of 511.09. That means that is the highest y value used on our parabola. So there's a little difference from just talking about a random graph and a graph that actually represents a situation. We have a limit to our domain and range now. Okay, so these questions are just talking about a parabola in general. Let's relate these values to the actual situation that the parabola is representing. So we're going to change these questions to words, but we are essentially, and if you think about it, hopefully some of these make sense. We are just referring to a lot of these key values that we discussed just above. So to start, we are looking at the question of what is the launch angle that yields the greatest distance traveled by these pumpkins? And so, a couple things to realize when we say launch angle, we are talking about an x value. Hopefully, that makes sense. And when we say the greatest distance possible, remember we had a maximum before, and that maximum came from our vertex. So, when we talk about the x value that's going to um, cause the pumpkin to go the farthest, that is going to be the x value of our vertex. The vertex is where the maximum occurs. So make sure that when you're looking at the vertex, you're giving the correct value here, knowing that our angles are the x values. So an angle of 43.208 degrees is going to cause that pumpkin to go the farthest. And if you read the next question, directly ties to it. What is the greatest distance? Realizing that this is a y value. What's the greatest distance traveled by these pumpkins? That again is your vertex. The vertex had the maximum value, so 511.09 feet. Okay, so the only difference down here is we need to realize words, the words that go with our variables. So we're not just talking about random x's and y's anymore. X's represent something and y's represent something else. And so to answer both of these questions, we looked at our vertex. So we related a point on our graph into the context of the situation. So we're going to try that a couple more times. We have a question here that says, what is the launch angle? So again, that is an x value. And what x value would cause the pumpkin to travel 0 feet? And 0 feet is a y value. So we are now talking about points that have a y value of 0. And you might notice we have 2. Those points are your x-intercepts. And so now we have to stop and think. Do we give both? Or does only one make sense? And if you think back, these are angles of release. We are not going to release a pumpkin from a negative angle. It doesn't make sense for us. We're not working with negative angles here. And so even though I have 2 different points that have a y value of 0, when we put it into the context of flinging pumpkins in the air, there's only one of these angles that actually makes sense. And so we're going to stay with this 87.423, and we are going to ignore the negative 1.008. A negative angle will not make sense in this scenario, so we won't use it. Okay, and so another question would be, according to the given information, the catapult launches pumpkins from 25 feet above the ground. The catapults must be on a platform or somehow raised above the ground here. Our model gets away from that just a little bit, not by much. And so we think back to, where would this 25 feet occur? Well, it'd be your starting height. And so our starting values begin on the y-axis. That's our as far back as we look in these scenarios. So our y-intercept deviated from 25 just barely, just a little bit. And we see that we had a y-intercept that had a y value of 23.209 feet. So our model is based off of a height of 23.209 feet above the ground. So that's the thing about a model, though. It's making an approximation, so sometimes it doesn't match exactly what's going on in reality. It's close, but in reality, our data is based off of pumpkins being thrown from 25 feet above the ground, and the model, it had to get away from that just barely, but it's still pretty good. So realizing here, though, To answer these questions, we are answering with things that we already know about. We know about the vertex, we know about x-intercepts and y-intercepts. Now we're just putting it into terms of the situation. Okay, and just a couple more things here. We are going to talk about the launch angles that cause the pumpkin to travel 300 feet. And notice here it says what two launch angles. So we are being told that there are two different angles that would cause the pumpkin to travel 300 feet. And then we know that based on the graph. If you go back to the graph, 300 feet would be a y value here. And we see there are two different points that have that y value. So that means there are two different angles that create this to happen, whatever these are. And so we're going to figure that out. We're going to figure out what these angles are, these x values. Well, it turns out this is something we could do by hand, but that's kind of the beauty of having a graphing calculator is it helps us out. So if we can just realize that these 2 points that we're talking about are arranged horizontally from each other, they both have the same height. We know how to write equations of horizontal lines. A horizontal line is just y equals some value. And in this case, we're interested in the y value of 300. So something we've never done with a graphing calculator before that we're going to try now is we are going to type in an equation of a horizontal line. And that equation is very simple. It's just y equals 300. And so we get a visual. Here's this line here going through the graph. And so we see there are two different places we cross the parabola. These are the 2 points that have that distance of 300. And you're noticing that Desmos is picking up on that. It will tell us where this line is crossing our graphs, our first graph. And so there's the nice thing about a graphing calculator. It can help you find these spots. And if we just click on them, we see there are these 2 points that have x values of 14.792 and 71.623, both with that height of 300 though. So these are there are two angles that in our model that create a distance of 300 feet. So we essentially actually, without realizing it, solved a system of equations by graphing. And this system is one we have not done before of a line and a parabola. So that's neat. But let's go record these degrees, 14.792. And 71.623. So there's the two launch angles that are going to create this distance. Last question for us then is to just recap on something we've already discussed. It says you have an equation, but there are some limitations to it because we are looking at an actual scenario. And so what we're saying here is the model had two solutions, and we wrote those solutions down. They were negative 1.008 and 87.423. And the question is, which solution is not applicable to this model, and why would that be? Well, we've already discussed that more than once. It doesn't make sense to use a negative value in our solutions. And the reason for that is a negative value, a negative x value would be a negative angle. And that's not something we are using here. And so why is that one not applicable? Well, this x equals negative 1.008 degrees is not applicable because a negative, we can just put this, a negative angle measure does not make sense. for flinging pumpkins. Okay, and so just a scope into the limitation of using our models here. We need to use values that make sense for the scenario. So that should be the end of our little exploration. Again, this is not going to be a main focus of our class, but something that we wanted you to see. So now that you have this, make sure you filled in everything you need. The only thing that you still need to do is insert your graphs. If you want to, go ahead and put them into this document in the spaces provided. Otherwise, just go to Google Classroom and attach those pictures as a file. You just upload them from your computer, and they should be right there waiting for you. Thanks for watching.